which I've just talked about, and a few other examples like resonance circuits, quartz crystals, and etc. So that covers 4.3. You may not want to get into too much detail here because basically there's not a lot of calculation involved. All that is in this portion is a lot of theory. Okay, so just basic understanding of concepts. From here on we move on to 4.4, wave characteristics. Okay, so 4.4 is wave characteristics. This is one of the more important portions of waves, as most of the exam questions are based on this portion. So you probably want to go through each of the individual subtopics in detail. So the first part, 4.4.1, you want to describe what's a pulse. So tell the students about a string which is attached at a fixed end on one side, and if you send a pulse across the string, what happens to the pulse when it reaches the end of the rope? So you want to tell them that the pulse will reflect back and it will change shape. It will basically reflect along the x-axis. So that's a pulse. Now if you have a series of these pulses, you will create a progressive wave, which basically travels and carries energy from one point to another. Energy, so what travels in a wave is energy. You want to make sure that the students understand that the particles stay in their respective position. Okay, so 4.4.2 is that state that a progressive wave transfers energy. Okay, 4.4.3, describe and give examples of transverse and longitudinal waves. So transverse waves, you can talk about water waves. Longitudinal waves, you want to talk about sound waves, and also probably draw out or explain to them what are the differences between transverse and longitudinal waves. In the exams, it should be sufficient for them to know that in transverse waves, the direction of particles is perpendicular to the direction of propagation of energy, whereas in the longitudinal wave, the direction of the oscillation of the particles is in the same direction as the travel of the transfer of energy. Okay. So an important concept here is how do you graphically represent waves in two dimensions. So usually what's done is there will be two graphs. One is displacement versus time graph, and another one is a displacement versus position. Okay, suppose this is a wave and the displacement time graph is given like this. Okay. Now these two graphs could be for the same wave, alright? But the difference is that this graph, displacement versus position, is a snapshot of the wave at a particular instant, right? So, for example, all these points are different particles on the wave, right? But displacement time, that shows how the motion of one particular particle on this wave varies with time. So for this part, okay, let's assume that the wave is moving in this direction. For this particular particle, you can see that as time progresses, the particle is going to move downwards. So which one of these particles could that be? Let's say a fraction of a second later, the wave would look like this. Okay, so for example, this particle, which started off at the equilibrium position at time t equals 0, it moved downwards. So we could be talking about particle P over here being represented on the displacement time graph. So stuff like this you want to elaborate to them, and also what are the pieces of information that you can grab from these two graphs. One, of course, over here, this would be the amplitude of the wave. Same here, this would also be the amplitude. Why? Because the vertical axis on both of these graphs are displacement. The distance between to crest on the displacement time graph is one time period. Okay, any 2 points which are in phase would have a difference of one time period. Right. And similarly on the displacement position graph, any 2 points on the graph, the distance between them would be one wavelength. Okay, so you have displacement defined here, amplitude. Okay, this here would be the period, wavelength. So another thing you want to define is the points, the salient points on a wave. So in a transverse wave, the wave actually looks like this. The wave profile looks like this. For example, in a water wave, you have the particles aligned in this pattern. So the topmost points here are called crests, and the bottommost points here are called troughs. Okay, and similarly in longitudinal waves, you do not have crests and troughs, but you have points of compression and rarefaction. So a point of compression can be represented as a crest on a graph like this. For example, if you had to represent a longitudinal wave which has a point of compression here, let's say we are talking about sound waves, and these are air molecules. So you would have a point of compression, then a point of rarefaction. So this here can be represented via a crest, and the rarefaction can be represented via a trough. Okay, so on and so forth. So you can also represent longitudinal waves in a similar fashion over here. Again, this point here is called a compression, and this point here is called a this corresponds to the low pressure area. So it's called a rarefaction. Okay. Now, when we have waves, for example, water waves. Water waves would travel like this, let's say. Waves traveling in this direction. So the waves, the line joining the crest of a wave over here, the crest of all points over here on the wave, and the crest joining, the line joining all the crests over here, the line joining all the crests over here. These lines will appear to move towards the right of the page. Okay, these lines are called wave fronts. The line joining all the crests, and of course the distance between each wave front is one wavelength. Okay, so the wave fronts can be represented with straight lines, whereas the direction of travel of this wave would be perpendicular to the wave fronts. So this here is called a ray, and these are called wave fronts. Okay. Then lastly, you have the relationship between wave speed, wavelength, and frequency. The wave speed is simply the speed of propagation of energy. Speed is defined as distance covered over time taken. So we know that one wavelength travels in a time of one time period. So one wavelength travels in one time period, and 1 over t is the frequency of the wave. So therefore we have the velocity or the speed of the wave equals the wavelength multiplied with the frequency. 4.4.9 is the last portion of this segment, where you have to state all electromagnetic waves travel with the same speed in free space and that they are transverse waves. So you wanna talk about the electromagnetic spectrum and the salient features of the electromagnetic spectrum, and you also want to describe why and how are electromagnetic waves transverse waves. So for example, you have the electric field. The electric field vector, it moves in a direction perpendicular to the travel of the wave, and also the magnetic field vector also moves in a direction perpendicular to the travel of the wave. they are all orthogonal to each other. The electric field vector, magnetic field vector, and the direction of motion. So that is why there are no particles involved here, but even then, that is why electromagnetic waves are transverse waves. For electromagnetic waves, you want to talk, like I mentioned, you want to talk about the electromagnetic spectrum and the salient features. You have visible light. You can give them, they need to know that all electromagnetic waves travel at the same speed, the speed of light. And probably remembering a few wavelengths of some of the broader spectrums would help. For example, you have red light at 700 nanometers of wavelength. Okay? And you have violet light over here at lambda equals 400 nanometers. Then this direction is increasing energy and increasing frequency. Okay? But the wavelengths will increase in the opposite direction. Right? After violet light, the spectrum of the electromagnetic waves, which has more energy, are UV rays. Then you have X-rays here with even more energy, and gamma rays with the maximum energy. And to this side, below red light, you have infrared. Infrared is the main heat carrying component of electromagnetic waves. Then below infrared, you have microwaves and radio waves with the lowest energy and the longest wavelengths. So yeah, so some of the salient features you want to discuss, and probably some uses of each of the components of the electromagnetic spectrum. So that should pretty much cover wave characteristics. Okay, the last segment of waves is wave properties, also another important section. Basically, this is describing three major properties of waves: reflection, diffraction, and diffraction. So, firstly, you want to explain Huygens principle to the students, whereby each, okay, let's say these are wave fronts for a wave traveling in this direction. Each point on the wave acts as a secondary source of a wave. So, for example, this point here is actually creating a wave like that. Another point here is creating a wave like this. Okay, so the wavefronts that we see, okay, of crests and troughs, that pattern is actually an interference pattern of all these individual wave sources. Alright? So this phenomenon is Huygens principle. So Huygens principle. Okay. So Huygens principle can be explained, can be used to explain all these three phenomena that we just talked about: reflection, refraction, and